Good morning, Dr. Nat here. We are doing Chapter 6, Part 3, the final part to this chapter. We are doing on gravitational force. And right now, I have a question for you. We are in space. What keeps the Earth orbiting around the Sun? Okay, so if you have an idea about this, you would answer, oh, it's easy. It's the force of gravity. Okay, so I have another question for you, Smarty Pants. What is the force that keeps the moon orbiting around the Earth? Is it still force of gravity? Is it a different type of force? What is it? So last time we learned about centripetal acceleration, right? And we know that centripetal acceleration is what keeps our V tangential to keep on changing directions, which gives us the circular motion, the circular path. So here, do we have centripetal acceleration in space? Yes, we do. But what is it? How do we calculate for this centripetal acceleration? Okay, so we will discover this in the next few slides. Let's continue. So next slide. So gravitational force. According to Newton's law of universal gravitation, I know Newton has so many laws, right? I mean, why? But really, we have to learn this because it is about the Earth. It's about the universe, okay? So Newton's law of universal gravitation states that the force of gravity is equal to G, where G is the universal gravitational constant, M is mass of object 1, M2 is the mass of object 2, and R12 is the radius between mass 1 and mass 2 squared. Okay? So we know that F is in newtons, that's the SI unit, G is a universal constant, mass is in kg, this guy is also in kg, and we have r squared, the SI unit for distance is meter, so we have meter squared. So rearranging this, I get my G as F12 R12 squared over mass 1 mass 2. So the unit for G is, it's Newton meter squared over kilogram squared. Is that the same? Yes, it is. Okay, so this value 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared is constant. It doesn't ever change. You will always use this value. Okay? Guys, this is serious. I'm in space and I brought two fruits with me, which is an orange and an apple. And my apple keeps orbiting around the orange. I know. Why, right? Okay, but I need to figure out what the gravitational force is between the apple and the orange. So using the Newton's gravitational law, which is this equation, I'm going to plug it in and find out what is the force of gravity between my two fruits. Okay, let's do this. So mass 1 is orange, mass 2 is apple. You can flip this around, it doesn't matter. So you can put this as mass of apple and this is mass of orange. Doesn't matter the which comes first. And then the radius between the orange and the apple must start from the center of mass. I cannot stress this enough. It must start from the center of mass of the orange to the center of mass to the apple. Do not start at the end from here to here. That is wrong. You cannot use this as your radius. The radius must start from the center of the the center of mass. Okay, so this is RAO or R apple to orange and it should be squared according to our equation. Okay, so this is the force of gravity between the apple and the orange. Okay, so G is a constant, so I'm just going to use it anyways. 6.67 times 10 to the minus 11. The mass of the orange. Remember, we always have to plug in SI units. So this becomes 0.058 kilograms. And my apple becomes 0.02 kilograms. The radius is given in centimeters. I also have to convert that to meters, right? So that becomes 0.2 meters squared. So the answer for this, if I'm using my calculator correctly, would be, using my trusty scientific calculator, the answer is 1.93 times 10 to the minus 12. And the units is, we are solving for force, it should be in newtons. Yes. Okay. Alright, so that is the final answer. Now, where is the direction of this force? So this is Fg. Fg is the force exerted by the apple on the orange, because gravity is an attraction force. So if the apple goes this way, this is my Fg, this is the force by the orange on the apple. Okay, because the apple is attracted to the orange, which means that the orange is exerting the force. If the orange is attracted, it's being pulled, which means that force is exerted by the apple on the orange. Okay, so that is how you figure out the direction. So here we can conclude that by Newton's third law, right, Fg by apple to orange and Fg by orange to apple is equal and opposite. Okay, so let's take a look at another example. Let's take a harder one. Not that hard, but a little bit harder. Okay, calculate the force of Earth's gravity on a spacecraft 12,800 kilometer, which is 2 times the Earth's radius, above the Earth's surface if the mass is 1350 kilograms. Let's draw this situation. We have Earth. The radius of Earth is RE, and a spacecraft that is 12,800 above the Earth's surface. So it says it's twice. So this is twice Earth's surface, Earth's radius. So this is where the satellite is. Whoopsie, bad drawing. Okay, oh, this is even worse, but never mind. Okay, so the satellite, just gonna try my luck. Okay, so that's your satellite over there. So the information that you have is the mass of satellite is 1350 kilogram. The radius of Earth is 12,800 divided by 2, which is 6,400 kilometers. And then you know that the spacecraft is 12,800 above the Earth's surface, which is 2RE. So the radius between the center of Earth, the center of mass of Earth, to the center of mass of the satellite is 3RE, right? So RE to satellite is 3RE, which is just 3 times 6,400 kilometers. If you didn't write this, if you didn't draw this, you wouldn't have seen this. So it's very important for you to try to visualize the question. I always tell this to my students. Always draw your question to get a clear idea of what you are trying to solve. Okay? So now let's plug in the values into our equation. So mass of Earth, mass of satellite over radius of Earth to satellite squared. So this becomes 6.67 times 10 to the minus 11 times with the mass of Earth I don't remember. Let me check. So it's 5.98 times 10 to the 24. And the mass of satellite is 1350. I need more space. Give me a minute. So times with 1350 kilograms divided by 3RE, 3 times 6,400 squared. So that is your force of Earth to the satellite, which is also force of satellite to the Earth. Right? Remember, Newton's third law equation says that force is equal and opposite. So this is whatever answer that is. Use your calculator, but that is how you solve it. Coming back to our first question for this part. What keeps the moon in a circular path around the Earth? Yes, it's the force of gravity. So that's the end of part 3, chapter 6. I hope you enjoyed doing chapter 6 with me. See ya!